ABC Calc. Today we have your day 78 notes. Today we're talking about the calculus of y equals a to the u. We know the derivative of e to the u, but what about another base? So we're going to get into that very, very quickly here because, as per usual, try these two questions. So given an accumulation function g of x, find g prime of e. Okay, think very carefully about what we're going to do to evaluate g prime of e for number one. Number two, looking like a great candidate for some good old logarithmic differentiation there, find dy dx. So go ahead and try those two. I'm going to jump right to the next page. And when we talk about the calculus of e, like we already know, if we're taking the derivative of e to the u with respect to x, we would have e to the u times du dx. And the integral of e to the u is e to the u plus c. So those are facts that we're very well aware of, I think, at this point. What I want to do is use logarithmic differentiation to find the derivative of each of these. And then by the end, we'll have generalized the pattern for something of the form a to the x. So let's take a look at the first one here, y equals 2 to the x. Logarithmic differentiation, let's take the ln of both sides first, bring the x out in front, so we get x ln 2 there, and then take the derivative of both sides. So here we're going to get 1 over y dy dx. And on this side, we get ln2 is just a numerical value, right? It's the coefficient of x there. So that's just going to be ln2 when I take the derivative of the right. So then if I take the y and multiply it over, I get dy dx equals y times the ln of 2. And oh yeah, well, y is really 2 to the x. So we get dy dx to be the ln of 2 times 2 to the x. All right, well, you guys can actually hit pause at this point and go ahead and try it for these other exponential bases. By the end, you'll have very quickly developed a pattern that we want to establish here, but I'm going to keep going. We get ln of y equals x ln 3. Take the derivative, 1 over y dy dx equals ln 3. Multiply the y over. And oh yeah, y is really 3 to the x. So here dy dx is the natural log of 3 times 3 to the x. You know where we're heading, don't we? All right, let's do it. ln y equals x ln 10. Derivative 1 over y dy dx equals the ln of 10. When I multiply the y over, I'll kind of shortcut it real quick and just know that y is 10 to the x. So here we get the ln of 10 times 10 to the x. And last but not least, we have y equals e to the x. So ln y equals the ln of e to the x, 1 over y dy dx. And here I was supposed to bring down that x, wasn't I? So that's going to be x ln e, which is just ln of e on this side. So then dy dx is the ln of e times e to the x. Oh yeah, and ln of e is really 1. So did I have to use logarithmic differentiation here? No. But I've actually seen some of you in class when you kind of have that moment of forgetting that the derivative of e to the x is e to the x using logarithmic differentiation. And I love it because you have the skills, right? So if you forget at some point how to find that derivative, then of course we can justify it using some good old log differentiation. So we know the pattern at this point, don't we? If we take a look at an exponential base of 2 and 3 and 10 and compare their derivatives, in general, the derivative with respect to x of the function a to the x is going to be the natural log of the base times the exponential a to the x, something of that form. And if we have y equals a to the u, where u is some differentiable function of x, here we would have still ln of the base times a to the u, but of course with our chain rule times du dx. So that's a pretty quick and hopefully easy rule for us to develop and justify based on trying it out with some logarithmic differentiation for a bunch of different bases there. So let's go ahead and try some practice on the next page. Find dy dx for y equals 8 to the x squared and y equals 10 to the tan x. I'm really hoping at this point in the game, now that we're up to day 78 here, right? When I teach you a rule, if you want to hit pause and try it, of course, I'd recommend that you do that on your own. But if you're like, yeah, I'm not really sure yet, let's just see a few practice problems. Well, then here we go. Dy dx for the first one. would be ln of the base, so ln of 8 times, this is a to the u, so it's going to be 8 to the x squared. But since u is x squared, we're going to multiply it by du dx. So the derivative of x squared, of course, is 2x. And as far as, how this should all be placed together to get a final answer that's cohesive here, I mean, I guess you could bring the 2x all the way out front, 2x ln 8 times the base 8 to the x squared. You might just have to look for alternate forms in a multiple choice style question, but anything along those lines would be a correct answer for number 1. So something of the form dy dx for y equals 10 to the tan x. Dy dx would equal, well, it's going to be ln of the base 10 times 10 to the tan x times the derivative of u with respect to x. That's going to be times secant squared x. And again, maybe I'll just even leave it like that this time. I don't think we necessarily have to rearrange there, but that would be the final answer for number 2. All right, well, now let's really quickly move on to integrating. If when we find the derivative, we are multiplying by ln of the base a, it will not be too much of a surprise that when we integrate, you will get the function a to the u divided by ln of the base a. And of course, indefinite integrals, we need our plus c here. So that very quickly then helps us to develop a rule for something like 5 to the x. The integral of 5 to the x dx would be 5 to the x divided by ln 5 plus c. Once we have this rule, we'll see that the practice does go fairly quickly. Now, in this next example, we have our exponential 8 to the x squared minus 1. Hopefully, you're recognizing that this would be a good u substitution such that the remaining pieces here are going to be a scalar of what du equals. So if I let u equal x squared minus 1, that exponent, then du would equal 2x dx. So if I want to get x dx, I'd have to multiply both sides by a half. So bring the 1/2 out front of 8 to the u du. So this is going to be 1/2 of 8 to the u over the ln of 8. And since u is x squared minus 1, for indefinite, you have to plug in for your u substitution again, right? We're not changing any bounds here since it's not a definite integral. So we get 8 to the x squared minus 1 over 2 ln of 8. And don't forget about plus c. Something along those lines there. Okay, so we've got some derivatives going. We've got some integrals. What I want to move on to now is talking about, we've been discussing things of the form a to the x, right? That's exponential. But that's not to be confused with power functions. And we're going to be talking at the end of the lesson about, how do we differentiate something when there's x's in the base and also x's up in the exponent, right? Is it exponential? Is it power? Maybe we're not really sure. Okay. Before we get into that, though, we've proven this power rule for differentiable functions in many different scenarios. We've proven it if, n is an integer. We've proven it for n being a rational number. But we haven't really talked about, well, what if n is irrational? Okay, so to prove that this rule does work for when n is an irrational number, let's let y equal u to the n. And then to find the derivative, let's go ahead and use logarithmic differentiation. So we know that ln y would equal n times ln u. And if I take the derivative of both sides, we're going to get 1 over y dy dx. On this side, we're going to get n times, well, n is just a constant, right? So we're going to have 1 over u is the derivative of ln of u, but times du dx. And then in the last step here, to get dy dx alone, I'm going to multiply both sides by y. Now, when I do that, I'm going to put y in a very specific place on this side, because remember, y is equal to u to the n. So since we have u in the denominator over here, I'm going to multiply the y to the middle term here. I mean, it's a product, so I can multiply y, wherever I kind of want there. But dy dx would therefore equal n times y over u, which remember, y is really u to the n over u, du dx. And in one last simplification step, we know if we have two things with the same base and we're dividing, we would subtract the exponents. So this becomes n times u to the n minus 1 du dx, matching exactly what we started with, which we know is proven true for rationals and integers and things of that nature. So yeah, I guess even if n is an irrational number, we can still use our power rule to be able to find the derivative. So let's go ahead and just apply that real quick. If we have something like x to the radical 5 power to find dy dx, we would have dy dx equals radical 5 times x to the 1 less power, radical 5 minus 1. And that's pretty much it. Same idea for number 2, but we've got some chain rule to work with there. So for number 2, dy dx would be, bring the exponent down, radical 5 times tan x. So now the radical 5 minus 1, but times the derivative of the inside, which is secant squared. So that should be pretty easy to find, and we shouldn't really have to question ourselves about what the rule is anymore when we're faced with something that's an irrational exponent like we see up there. And finally, to bring us back to the discussion that I have at the top of the page here, is it power versus exponential? At the top, I have the two different forms. That power is something where the base is a variable, like x to the n. But exponential, we know that the base is numerical and the exponent is up in the variable. So that's something of the form n to the x. So then here we are, x to the x. What do I do? How do I find the derivative? Am I going to use the power rule? Or am I going to use the rule that we have for exponentials that we talked about in today's lesson? Well, it turns out that it's not really either of the two. So the only way to go about something like this, if you can't really tell, is it power, is it exponential, there's x's in both locations, is of course good old logarithmic differentiation. That's it. So we take the ln of both sides for number 1, ln y would equal x ln x. And then we're going to take the derivative of both sides. So the derivative of ln y, done that a few dozen times at this point, 1 over y dy dx. And then x times ln x, we know that we're going to have to use some product rule there. So the derivative of x is 1 times ln x, plus the derivative of ln x is 1 over x. 1 over x times x is 1. So that right side becomes ln x plus 1 after using the product rule. Multiply the y to the other side. Dy dx equals y times ln x plus 1. And in the last step, of course, we can replace y with x to the x power. So you'll notice that it's not really a result of just saying, oh, bring that power down and reduce it by 1. Nope, that's not what we get in the end. And can I just think of this as, using the exponential rule from the start of today's lesson? No, not quite either. So you do want to use logarithmic differentiation for something like that. Okay. If you want, go ahead and try the last one. I'm going to do it with you real quick now. So take the natural log of both sides, bring that exponent of tan x down in front of ln x. All right, derivative of both sides, 1 over y dy dx equals, again, product rule on this side. The derivative of tan is secant squared, so it's sec squared x ln x, plus the derivative of ln x, which is 1 over x times tan, so that's tan x over x. And then when I multiply the y over, dy dx would equal x to the tan x, I'll make that replacement right away, times secant squared ln x plus tan x over x. Okay. So we'll be doing a little bit more practice with that, where if it's not necessarily power or exponential, then we can still use some logarithmic differentiation to find the derivative. And other than that, we are really building in chapter 7 here. We now have the derivative of a to the u. Get ready for some more log-based derivatives in the next coming lessons. Have a great rest of your day.